Hi, my name is Evelyn Moss, and this is my Physics 2112 Lab 3, Black Hole and Orbits. The purpose of this lab was to analyze the star's motion to find the net force on the star for all points in the dataset using the scaffolded starter code to estimate the mass of a black hole. The second part of this lab, the purpose was to find the initial velocity of a spaceship that allows it to go in orbit without hitting the moon. The fundamental physics principles used in this lab would be Newton's second law, universal gravitation, circular motion, and update formulas. Newton's second law, also known as the momentum principle, is where a net force is equal to the change in momentum over the change in time, and this is expressed in the equation below. Universal gravitation is a formula that calculates the gravitational force between two objects using gravitational constant g, which is equal to 6.7 times 10 to the negative 11, and this is also shown by the formula below. For circular motion, net force can be determined from adding the parallel and perpendicular forces together, as shown in the equation below. And the update formulas are final velocities and positions of an object at a given time can be found using the velocity and position update formulas, the velocity on the left and the position update formula on the right. A preview of the results of this lab would be that after using two GlowScript simulations, we were able to analyze and estimate these values. The mass of the black hole to be 1.150796 10 to the 24 kilograms, and the initial speed of the spaceship to be 27,000 meters per second in the x direction and 24,000 meters in the y direction. The initial conditions for part 1 of the lab are shown below, with the gravitational constant, the mass of the star, and delta T being the number of seconds in a day. The system for this part of the lab would be the black hole and the star, and the surroundings would be the space and the things that exist in it. So here's the loop in our GlowScript code. We can use the initial and final velocities to calculate the change in momentum, which we can then use to find the Fnet by the momentum principle. Once our code did those things from Fnet, we could then calculate the parallel and perpendicular components of the net force to use in the gravitation equation to find the mass of the black hole. And by taking the average of all the computed values run throughout the loop, the mass of the black hole was found to be 1.150796 times 10 to the 24 kilograms. For part 2 of our code, the initial conditions are given on the right, and the speeds that are in the initial conditions were found through trial and error. And the system for this part of the lab would be the planet, the moon, and the ship, and the surroundings would be space and all the things that exist in it. All right, and for the loop in this part of the code, first we found the gravitational force on the moon by both the spaceship and the planet, and then summed them together to get the net force on the moon. We repeated this process, switching the variables where needed to calculate the net forces on the ship in the next part of the code. With these values, the velocity and position update formulas were then used for the ship and the planet. From there, the code could run the orbit as long as the initial velocities or the initial speeds allowed for there to be no crashes between the ship and the moon. The results of the orbit, or the results of the code are shown below, and the speed of the ship that allows for a non-collisional orbit would be 27,000 meters in the x direction and 24,400 meters in the y direction. Some sources of error in this lab would be rounding errors and then just some guess and check errors. Since this lab was all simulations, there was little to no room for physical human error, but like I said, there are some possible sources of error present. The rounding errors just through the program gave potentially rounded things that gave inaccurate values that could manipulate the black hole's mass or the orbit's mass in part 2. And then the initial speed values in part 2 were also found through guess and check, and this could provide an orbit that causes no crashes. And as this did provide an orbit that caused no crashes, there was not the perfect speeds to create a figure 8 orbit. All right, now for the discussion. The what does it mean question. How are the net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components? The answer would be they are related through momentum principle but are calculated differently. For net force, you need to account for all the interactions in the system to find the net forces, whereas with momentum, you only need the change of velocity and the mass. The what-if question is, if you wanted to predict the motion of the entire system, what would you need to include in your computational model? Would there be any dominant interactions, or would they all contribute more the same the less? The answer would be that we would need to calculate the net forces for the moon, the planet, the star, and the black hole using their initial position and masses. The black hole would most likely act as the dominant force. Because of its size, it will have the largest influence on net force.